Okay, we're back to finish up forces. Just move this up a little bit more. There we go. Okay, so far we've talked only about the force of gravity, or weight, they mean the same thing. We've got 5 other forces that I want to talk about before we get into free body diagrams. So, I'm going to just kind of divide this off so that we don't get confused. Okay, next force we're going to talk about, and all these forces are the same that you did talk about last year. So next force we're going to talk about is, symbol is Fs. This is the spring force, with the equation being similar to last year, but with one key difference. Fs is equal to negative Kx. K is your spring constant. Spring constant is different for every spring, and essentially what it does is tell you how stretchy or how hard it is to stretch that spring. A low spring constant means it's very easy to stretch. High spring constant means it's very hard to stretch in terms of how much force you have to put on it to stretch at a certain distance. The units are newtons per meter. So if you have a spring constant, spring with a spring constant of 100 newtons per meter, what that means is for every meter that you pull this, that you extend or stretch the spring out or compress it, that takes 100 newtons of force to hold it at that spot. So you want to hold it 1 meter. If you want to extend it by 1 meter and hold it there, you need a force of 100 newtons to hold it there. That's what 100 newtons per meter means. The variable x refers to the distance that the spring is stretched or compressed. Okay, and the reason that there is a negative there, that's kind of the other important part. Last year you just did Fs equals Kx. The reason that it's negative is because the force and the amount of stretching or compression are in different directions. So in other words, when you try and stretch a spring out, what does the spring want to do? It wants to go back to where it wants to go back to normal. If you try and compress a spring, it wants to expand back out towards normal. So whether you stretch or compress it, the force from that spring is in the opposite direction. So if you extend a spring down, the spring will pull back up on whatever it is that's making it move down. Okay, so there's the spring force. Pretty straightforward as far as forces go. Next, we're going to be talking about the one that is symbolized by T. This is tension. And you can write Ft if you want. I usually just call it T, capital T. And this, whenever you see tension, this is a very simple one. It is the force of a string or rope or cord that is holding onto something, that is attached to something. There is no formula for tension. It is one of those forces where you have to determine the magnitude of the tension in comparison. You have to determine the magnitude of the tension by drawing a free body diagram and understanding the size and the magnitude of the other forces around it. There is no one formula for tension. So that one is actually pretty straightforward. Next, we've got Fn, not the net force, that's F net. Fn is the normal force. And what the normal force is it is a contact force that is always perpendicular, that's the perpendicular sign, to the surface between two objects. So for example, the calculator has a normal force on it from the stand that points straight upward, perpendicular between the surface. The surface between them is this flat surface. The normal force points upwards from that. A lot of people usually start thinking that the normal force always points up, and that is not true. If I were to put my hand on the wall, on a vertical wall, the normal force on my hand from the wall is outward. Because it has to be perpendicular to the surface between the two objects. If I put my hand on the wall, the surface between the two objects is vertical. The normal force couldn't also be vertical, because then it wouldn't be perpendicular to the surface where my hand and the wall are touching, so it has to be outward. If you have a ramp, the normal force is tilted at an angle that is perpendicular to the ramp surface. So that's just something to remember. We'll talk more about that when we get to ramps in the next set of video lectures. All right, the next one is the applied force, that is FA. This is another one that people get confused on a lot. The applied force is simply the force a person, can't read my own writing, exerts by pushing or pulling or kicking. However a person exerts a force on something, that is the applied force. So it has to be a person. A lot of times the way people get this messed up is they assume that anytime an object is moving, it needs an applied force. That's not true. A hockey puck that's sliding over ice with no stick pushing it, a stick attached to a person, does not have a normal force on it. It did when it got started moving, but now that nothing is touching it, there is no applied force acting on it. Okay, so not every moving object has to have an applied force. Okay, so there's 4 more forces. That takes us to the last one, which is probably the most complex force that we're going to deal with at this point, and that would be the force of friction. Okay, so there's a lot of different things that you need to know about the force of friction, so I'm going to take my time going through it. First of all, there are 2 types of friction. Okay, and by the way, when we talk about friction, we are talking about a model of friction. We're talking about how we can understand friction on kind of like a first approximation. It is actually much more complicated than this, but for most purposes, at least for the purposes of this course, we're going to treat friction according to this model. Okay, we're modeling what happens in the real world. So anyways, there are 2 types of friction. That would be kinetic friction. Remember, kinetic means something in motion, so friction for something that is moving. And static. I'll just put in motion. And static, which means at rest. The force of friction that occurs when something is at rest. Okay? Now, typically, and I've always seen this be the case, whenever we talk about static friction versus kinetic friction, static friction usually has a greater magnitude than kinetic friction. And the way I like to think of this is it is harder to start motion than to sustain it. It's much harder to get something to start moving than it is to keep something moving once it is moving. And the reason for this, it's at the intermolecular level, friction arises due to forces between between molecules and atoms. We all know what they're made up of: neutrons, protons, and electrons. And when you have 2 objects that are really close to each other or touching, what happens at that lowest level is there are electrostatic forces between the different types of particles. And electrostatic force is actually a force we're not going to talk about right now. We won't worry about that until the electricity unit. But in any case, the electrostatic force, what ends up happening is when an object is at rest relative to some surface, what might look like a smooth surface to us is really in reality not. It's a very jagged surface. What happens when something comes to rest is the 2 objects, they sort of settle into one another. Okay, so you sort of have, I mean, if this is one surface, this is a real exaggeration, this is another. If they're at rest, they're kind of settled like this. Now, if you try to push the object, because the objects are kind of settled, these very jagged surfaces are kind of settled into one another, it takes a lot of force to do so. Okay, it takes a lot of force to break those, to get one object kind of out of that groove and then moving past it. Once the object is moving past it, it's much easier, okay? That's not as settled. It's much easier for the forces. It's much easier for a smaller force to keep that object moving. So that's a really very, very, very basic picture of what's going on at the smallest level. What you can think of it as is, again, these two objects that might seem to have smooth surfaces are not really smooth. They kind of get locked into one another, and to get them started to move, it takes an awful lot of force. Once the object is moving, now they're not as settled in. It doesn't take as much force to keep them in motion. So that is why static friction is usually greater than kinetic friction. Okay, now there just in general, okay, the direction of the force of friction. Friction is directed, not direction, in the opposite direction of the motion that would occur without friction. So in order to figure out what direction friction points, you think about what would happen if there was no friction on the object. And this can be kind of complicated sometimes. You might need to know how big the other forces are. So, I lost my train of thought for a second. So what you need to do in order to figure out the direction of the force of friction is at first pretend that there is no friction. Which way would the object move or try to move, and friction points in the opposite direction as that. Alright, a couple more things. There's an equation for the force of friction. That equation is Ff equals mu times Fn. That symbol right there is a mu. Hopefully, yep, okay, you can see that. Now mu stands for the coefficient of friction. If the coefficient is higher, as you can see from the equation, that means there's a greater force of friction. Okay? And the last thing I want to talk about friction is this equation is only good for calculating kinetic friction, if something is moving, or the maximum amount of static friction. Now, the reason for that. Static friction can have any value up to a certain point. There is something called the maximum coefficient of static friction. Take this calculator, for instance. If I try to push on this calculator, I'm pushing very, very lightly, okay, then it's not moving. What that means is, even though I'm pushing this way, there must be a force of friction that resists my motion pointing this way. If I now try and push a little bit harder, it still doesn't move. So what does that imply? It implies the force of static friction increased to still balance out my force of friction. This is true up to a point called the maximum force of static friction, the biggest that the static friction can be. After you put a force on the object that is greater than that and try and get it to move in a certain direction, the object will start to move. And now we're dealing with kinetic friction. So this equation is good for calculating the kinetic friction or the maximum amount of static friction. If it's below the maximum amount of static friction, then the force of static friction is simply equal to however big the force is that's trying to get the object to move. That's a very tricky concept, and we'll see that a couple of times in our problems. Okay, what I'm going to move on to now are the steps for a free body diagram. Let me move this down just a little bit. I can actually read it. Okay, now why do we care about free body diagrams? Why do we study them? The reason we study them is because they are a method of analysis for forces. This is how you determine how the forces act on an object when there could be many forces acting on the object in order to produce a certain acceleration. Just like in kinematics, what we did was we wrote down all the values that we knew, and then we tried to figure out how to apply equations to that. A free body diagram is simply our way of getting ready to do a forces problem so that we can determine the net force and the acceleration. So what we're going to do here is I will give you the steps. The steps are pretty much the same as last year for drawing a free body diagram, and then we will carry out those steps on this example. The example is a child exerts a force F at an angle of theta to pull a sled of mass M along a straight level path. There is friction present. Draw the free body diagram below and write the net force equations for both the horizontal and vertical directions for the sled. Our first step for any free body diagram at this point is to draw and label a dot as your object that you are trying to analyze the forces on. Very simple, takes 2 seconds. So, in this case, I would draw a dot, and I'm going to label this dot sled. Okay, that's the object that I'm studying. The next step. Just like in some of the projectile motion questions where we had to specify which direction was positive and negative for x and y, we need to draw in an axis for our free body diagram, showing positive x and positive y. I'll put that right there. We'll do the standard. X to the right, y up, just like that. So, those are the first 2 steps. They take approximately 5 seconds. Now, we actually start the physics. We draw in vectors for each force. And there's some notes that go along with this, okay? Any vector that you draw must start on the object, okay? Vectors don't start off the object in this case, they start on the object, and you draw them, or they extend in the direction of the force. So, for instance, this sled has a mass of m, and we can assume that it's on Earth. That means Earth is exerting a force on it, the force of gravity, that points downward. So we would draw the force of gravity in like this, and write Fg. Okay? I can draw some other forces in, but before we do that, we'll do some other little notes that you need to be aware of. If there is a bigger force, that means you should draw, if this is a scaled diagram, a bigger vector. Now, we don't know the size of these forces, so I'm not going to scale this, but if this was a scaled free body diagram, or you were asked to draw a free body diagram to scale, a bigger force requires you to draw a bigger vector. The other forces that are acting on this that I want to draw on right now, it's on a straight level path, so it's on a flat surface, which means that between the sled and the surface there must be a normal force. And that extends upward like this. I label it Fn. There is friction present. Let's say the sled is moving to the right, just for the sake of keeping this easy. If the sled is moving to the right, that means friction must point back to the left. So that's Ff. I have 3 more notes. The next one is a big one, especially this year. Any forces that are diagonal need to be split into components. And we practiced doing that just recently in the kinematics notes, splitting a vector into components. Now, the force that's at the diagonal here is this force F, the force from the child. So I'm going to draw it like this, okay? F, and it says that it's at an angle to the horizontal. There's our angle. Now, what direction is F in? You might say, well, it's in somewhat the x direction, somewhat the y direction, but that's not good enough. I want to know, if I'm going to eventually write net force equations, I can't have any forces that aren't exactly in the x or y direction. So I'm not going to get rid of F, but what I'm going to do is split it into components. With our standard, okay, since our angle is measured relative to a horizontal line, that means that the x component is going to be given by F cosine of theta. And the y component is going to be given by, let me just make this a little clearer, F sine theta. Now, when I ask what direction is F in, it doesn't even really matter. I can say, well, there's a component in the positive x direction, there's a component in the positive y direction. That is why we split things into components. Okay, so diagonal forces get split into components. 2 just little pointers before we get to the net force equation, since we're pretty much there. You do not draw forces that this object, in our case the sled, exerts on other objects. So for example, we don't put the force of the sled pushing on the ground because the ground is not the object we're studying. We don't put the force that the sled puts on the kid or the child because the child is not what we're studying. We're studying the forces on the sled. Okay, yeah, draw free body diagram below and write net force equations for the sled. And then finally, objects can't exert forces on themselves. Themselves, if we're being proper with our grammar, I think. Okay, so this sled can't put a force back on itself. If it were able to do that, the sled would be able to accelerate just out of nowhere, and that would break all sorts of laws like conservation of energy and so on and so forth. What we're going to do now is we're going to write out the net force equations. Once you've got the free body diagram, this is easy. The net force equation in the x direction, so F net x, is just the forces that are in the positive and negative x direction. Positive x direction, we have F cosine theta. Negative x direction, we have force of friction, so we're going to put minus FF. And since it's a net force, we always write at the end equals MAX. Now here, we have no info about if this object is accelerating or not. So what we're going to do is leave this equation the way it is. Next, what we're going to do is we're going to do the net force in the y direction. That would be F net y equals, in the positive y direction, we have Fn and F sine theta. Those are both in the positive direction, so we're going to put plus signs in front of both of those. In the negative y direction, we have Fg, so we're going to put a minus sign in front of that, equals MAY. Now this time, we can actually make an assumption here. Since this is on a straight level path, and it doesn't say anything about the sled being suddenly picked up off the ground and accelerating up into the sky, and it's very clearly not burrowing into the ground, we can assume that there is no acceleration in the y direction. In other words, AY equals 0 meters per second squared. So what I can do is actually cross this off, write 0, and now I can rearrange this into Fn plus F sine theta equals Fg. And this is interesting because we were not told that the acceleration was 0, but we inferred it based on the situation. And this is interesting because a lot of times in Regents physics, a lot of people would say, oh, Fn always equals Fg. We see that that's not the case here because of this extra upward force. And we'll see a lot more cases of that as we go. That's the basics of forces and free body diagrams. Hopefully you refresh your memory on how this is going to work. I'll be back in a little bit to talk about forces on a ramp.